Hi everyone, this is Madhav, and this is a more complex video. I'd say you probably need grade 11 math, understanding what functions are and what vectors are before you understand this video. Just keep that in mind. And that being said, this is a presentation I gave at the university. It was related to some cool algorithms I've been learning about that try and mimic nature to solve problems regarding cybersecurity. So let me just give some context about that and we'll dive into the details. So the context is that I've been working on the student design team at the university, specifically this team. It is trying to use AI algorithms to solve cybersecurity challenges. In particular, this particular team tries to prevent smart devices from being hacked. And these are things that you may have used in your day-to-day lives, things like Amazon Alexas or Google Homes. But it also is more, let's say, critical smart devices, things like a security system, a security camera at a vaccine production facility. So this is kind of important. We don't want those critical devices from being hacked so that, vaccine production stops or food processing stops or water treatment stops. So kind of a big deal. The issue was, even though we cared about this problem on the team, it wasn't so obvious how we would just take the AI algorithms we'd all heard about and then shove it at this problem. The issue is the scale of power that we're using. Most AI algorithms, they run on very advanced computer chips that can draw over 200 watts of power for one chip. Some AI algorithms, they use, thousands of these chips while training. In contrast, the devices we're working with are small microcontrollers. They're closer in power usage to our brains, maybe around 10 watts of power use, if that, that's the upper limit. So clearly there's like an order of magnitude difference between the conventional algorithms we would apply in most of AI versus the kind of intelligence we needed being closer to biological intelligence, because we only had biological intelligence worth of power to work with. So this kind of forced our team to stop. We couldn't just take what was obvious to us and throw it at this problem. That's when we were like, hey, if we gotta meet the power constraints of biological intelligence, why don't we take a look at algorithms that are based on how biological intelligence works? That's kind of how we got started exploring, and that's what led to this talk, where I'm going to tell you about two algorithms. One is based on how fish in flocks, or I guess schools, how they show swarm behavior, how one fish is influenced by the fish around it, so that the entire school of fish can come and find food. The other algorithm is based on societies, wolf societies in particular, how they have leadership, dominance, hierarchy, and how that helps them hunt. So let's dive into some of the more math details now that you have some context about the talk. So the first thing to keep in mind is that when we're talking about these algorithms, we're going to abstract away from the problem of cybersecurity. We're instead going to talk about function minimization. It turns out CS and engineering folks are very good at turning very messy real-world problems into a simple problem of which parameters, I guess, which inputs do you send in to the function so that the output is as low as possible. So for example, in this case, the function minimization problem, let's say you picked, this frowny face input, that's the value you picked for X. Not such a great input if you're trying to minimize the function, because you can see the function has a very high value for that input. In contrast, this smiley face, that's much better as an input because it leads to a much lower output. And the star-stuck phrase, that's the best input that we could find because it has the lowest possible output value. So we are trying to come up with algorithms that will take some function and then figure out what is the best or, approximately the best value to send into that function so that we minimize the output we're getting. This may sound abstract. I will give a very oversimplified and glossed over version of how this might relate to cybersecurity. So in the cybersecurity context, what you could have is you could take the data coming in a network request to the smart device. Then you could create a function on that data. The function takes in the data and it's supposed to return the probability of the network request being sent by a hacker. So let's say it outputs 1, then the function would be 100% probable. It outputs 0, it would be like, okay, no, the hacker, this is not a hacker, this is just a normal user request. So that's an example of how we can take, some messy real world data and turn it into functions. And when we combine functions like the ones I just explained, we can get, this function minimization problem instead of dealing with how do we detect hackers. So now, how do we actually minimize the function? How do the algorithms work in common details? Most AI algorithms, they use calculus magic. Now, calculus magic, people have different understandings of calculus. So, throw in whatever words you want, slope, derivative, gradient, whatever. But if I just oversimplify it, the algorithm will pick a guess for the input that will minimize the output. Let's say it's this frowny face. It will figure out with calculus magic, slopes, derivatives, gradients, whatever you want to say, it will figure out which direction is down. In this case, this direction is down. So then the algorithm will update its guess to be more down. So it ends up with a second guess over here. Again, more calculus magic, this direction is down. And the algorithm will eventually get stuck here because, well, this is where the slope is 0. It's at the bottom of a hill. This is the downside of traditional AI techniques, or I should say common AI techniques, because the algorithms have a tendency to get stuck in what is good, approximately. This is a lower value than when we started, but it's not the lowest possible value. It's not really even close. The way we get around that with bio-inspired AI algorithms and reduce, how much calculus we have to do because it's hard, it takes computational processing power. The way we get around that is trial and error, basically. We mimic the process of evolution in nature. In evolution, you just have a bunch of individuals, just throw out a bunch of guesses at which genes are good. You can evaluate the fitness of each guess. So some not so good, and others, more smiley faces. Those are better. And then finally, you just have survival of the fittest. The solutions that are not good, they die off. You get some more, individuals being born, and you just repeat the cycle. Evaluate their fitness, kill off the weak, and over time, hopefully you have a bunch of guesses that are, close to the global optimum, but hopefully at least, in a local optimum. So that is a bunch of calculus 101. Just keep in mind that the key idea is you're throwing out a bunch of guesses with the intention of just randomly over time stumbling into a good solution, and you get rid of the bad solutions as you go. So with those, side details out of the way, let's dive into the meat of the algorithms. First, let's talk about the fish related algorithm, which is actually called particle swarm optimization. because it looks at swarm behavior of fish. It's also similar to a flock of birds. So as you can see in both these examples, you have these complex movements from the groups, these complex movements that are created by just individuals following simple rules of behavior. And that's kind of what we call swarm behavior. How does this actually look like in the algorithmic sense? How do we take inspiration from this movement of fish or, movement of birds? Well, take a look at the dots on the screen. You can see how this looks a little bit similar to the fish we just saw, how they were swarming around. So the dots, they represent different guesses, like in the picture we had before. And the guesses, they are trying to converge on some of the points, metaphorically speaking, that lead to more food, like the fish are. So that's kind of on a conceptual basis, on a visual basis, the similarity between the school of fish moving and these dots moving around until they find the best feeding spot, quote unquote. We'll get into, what these things mean now in mathematical detail. So each of these dots represents, let's say, a fish, or in general, just a particle. You have p particles, the first, the second, the ith, the pth particle. And each particle, it will be associated with some kind of vector or list of variables. So the vector in our case, just prior, it could be where are you on the x direction, where are you on the y direction. So it could be a vector of position. And this vector is sent into the objective function f. The objective function f is, as we mentioned earlier, what we're trying to minimize. So we're trying to figure out what is the best position for a particle to be in so that the output of the function is as low as possible. Now, as I said earlier, each of the particles will have a position. So the ith particle, it has some x coordinate and a y coordinate as part of its position. But note that the position changes over time. As you saw, the dots are moving around the grid. So we have to make the position vector a function of time, and the x and y coordinates a function of time as well. This is the same thing with the velocity of each particle. The ith particle has a velocity with an x component and a y component. Again, if this velocity changes over time, so the velocity is a function of time. That's kind of the basic. So each of those dots we saw on the screen earlier, when we saw them moving around the grid, they were moving because their position was changing, and the position was changing because their velocity was changing. So for each particle, this happens. The question becomes, okay, how do we relate these two? Well, it's very physical. Just like kinematics equations you might learn about in high school, the new position at 11 seconds, it's based on the position at 10 seconds plus whatever the velocity is. So take the old position over here, and then old plus velocity is equal to the new position, just like kinematics equations. The velocity, that gets harder to update. That equation is more complicated, so we'll look at it step by step. The first thing to keep in mind is if we're talking about how do we update the velocity of the particle at, let's say, 11 seconds, well, the particle, it's not like some theoretical thing, it's supposed to represent fish. Fish have some weight, and when objects have weight or mass, then we have this thing called inertia associated with them. That just means if a fish is moving along in one direction with some velocity, it doesn't tend to change that velocity, it doesn't tend to change that direction of movement. And this effect is more pronounced when the weight W of the particle or the fish is higher. So W is just, some real number between 0 and 1. And this is the fish's or the particle's prior velocity. So that's one component of how we update the velocity. Some of the new velocity is based on some of the old velocity. But keep in mind, we're not just, throwing cannonballs in the ocean. These are fish. They are intelligent. They remember, where did I go to get more food in the past? So we're going to add in another component of this equation, which is the cognitive component. So each fish has a personal best feeding position that it remembers, where it found the most food. And the personal best for the ith fish, it is across all of the time that it's been moving. So what we're going to do is we're going to figure out what direction do we have to go in from the fish's current position to get to the personal best. That's what this subtraction does. R1 is just a random number between 0 and 1, and C1 is a measure of how strong the fish's memory is. So if we have a larger value for C1 here, a larger real number here, then the fish will be influenced more by what it remembers to be the best feeding positions it's visited in the past. So now you can see we have the physics of how the velocity is updated. We also have some, I guess, fishology, ichthyology, I think it's called, where depending on how strong the fish's memory is, it might, tend to go back towards positions it remembers there was a lot of food in. But keep in mind, though, we're talking about fish in a swarm. So some fish, like whales, some species of whales in particular, they might tend to have more desire to, go veer off from the rest of their group, their pod. Whereas other fish, like, let's say, tuna or salmon, they might have more of a tendency to stay around their flock. So we need to measure, how much is the social capacity of the fish that we're modeling. How much is that to be able to follow their swarm instead of, remembering for themselves where do we want to go based on where, good feeding positions. So we also have this social component, that's the last component, where we're looking at the global best across all fish, across all time. What is the best feeding spot found? This subtraction, again, it produces the direction that the ith fish must go in to get to that global best feeding spot. R2 is another random number, just to add in some diversity so the fish aren't all behaving the same. And C2, it's another constant that we would raise for fish that are more, swarmy. They like to follow the group, versus lower for fish that tend to be more independent. So these three components, they are being added together, where we adjust W, C1, and C2 to control how much does the physics, the personal, memory, and the social dynamic of the particle we're modeling or the type of fish we're modeling, how much does that contribute to how the velocity changes over time? This seems very vague and abstract. So let's look at some visuals so that, it's easier to work with. So summary, now let's look at visuals. When we are looking at the function f of x and y, you can see x and y, they are the inputs that we could choose. And f of x and y, it's represented by the shape over here, this 3D shape. What this represents is the height of the output that we're getting. If it's, taller, that means we're getting a larger value. If it's smaller, then we're getting a lower value. This can be condensed into this nice looking type of graph. It's fancy words called a contour plot, but you can think of it like an ocean. So the yellow parts over here, they represent the beaches. Those are, not very deep. As we get deeper and deeper colors, we're looking at lower spots in the ocean. And that corresponds to the minima of the objective function. So we'd ideally like the fish to go towards the minima. That's the problem we're trying to solve. Each fish, it represents the inputs that we're sending into the function, the colors represent, what is the output. So with that being said, take a look at some animations. Here, what we've done is we have fixed the cognitive and social components of the fish so that we can explore the effect of the weights. So when we have, the weight to a very small value, you can see that the fish barely are moving. They're moving very, very slowly because they have very little inertia. When we have the weight set to a very high value, you can see the vectors that represent the velocity. Those are really, really large. The fish will end up going in one direction, they'll overshoot, and then they'll have to come back because their inertia is so high, it makes it hard for the fish to change direction. In the middle, with the weight set between 0 and 1, here you see a balance of the fish not moving too slowly, but also not overshooting as they try to become closer towards the minimum point, the deepest point in the ocean. Now, let's look at the effect of varying the cognitive and social factors. So if we look at the weight being fixed now, let's say we set the cognitive factor, C1, to be 0 and the social factor to be 2. As you can see, the fish are moving quite erratically towards, this best value over here. Whenever a great solution is found by some other member of the swarm of fish, all the fish now suddenly move in that direction. You don't have much randomness, it's just everyone moving close to, identical directions. If we do the reverse, we set each fish to have a large cognitive factor. They remember their best feeding spots, but they don't care at all about the social aspects. Then what you see is the fish are, they're basically spread out. Each fish just sticks to the best location it found. It's not trying to get closer towards the best locations that the rest of the swarm found. So this particle swarm optimizer, it's used for many, many things, but in our case, it's used for cybersecurity. One of the things that we could do with it is what we talked about. We could take an algorithm that, has some network request coming in, and we could figure out probability, glossing over, oversimplified. Is the algorithm predicting the cyber attacks that we want, or is it just being wrong? If it is being wrong, well, algorithms, just like a particle swarm optimizer, they tend to have parameters like W, C1, C2. We can actually make this algorithm search for parameters of another algorithm. Maybe an algorithm that has a lot more parameters, things like neural networks, so that with this behavior, when we only need to adjust 3 parameters or 3 settings of the particle swarm optimizer, it's not too difficult, so we can do that. But if it was something like a neural network that was very complicated to adjust, we wouldn't need to like select 1,000 settings for that. We could just let the particle swarm optimizer pick those settings so that the end function that we wanted, the probability predicted thingy, it had the lowest error possible, or it had the best probabilities for the most accurate probabilities for, is this network request a cyber attack or not. So that does it for the particle swarm optimizer. And now we're going to move on to the gray wolf optimizer, the algorithm based on how wolf societies they go about hunting. So gray wolf optimizer, it's based on the hunting behavior of packs of wolves. These wolf packs, they usually live in groups of 5 to 12. And the way that these hunts work, they have 3 main stages. In the first stage, you just have a bunch of wolves that are, follower wolves, subordinate wolves, low-ranking wolves. They're just trying to follow the alpha, or, In some cases, the alpha and the beta and the delta. These are the lead wolves, the highest ranking wolves. The following wolves, they don't make any decisions at all. They're kind of spread out, far away from the alpha, and the alpha is quite literally on the prey's tail. So the lead wolves, they are making the decisions about where should the hunt go. Over time, the followers and the lead wolves, the alpha, beta, and delta, they close in a lot more. So as the hunt progresses, all of them are now hunched up around the prey, and the hunt finally ends when they have all encircled the prey so that the prey can't escape. So the wolves start far apart, converge in slowly, and eventually circle in on one single point. We're going to be using this behavior in the same way that we were using the the particle swarm optimizer. The movement of the particles, it was correlated with different guesses that we wanted to make for the inputs of the function. And the movement would lead to some inputs that had a lower output value. So in this case, we're going to, again, create a GIF to help show that, I guess, mathematical analogy to these three phases of movement. So here you see the wolves, the dots that represent wolves, they start off spread apart. As the hunt progresses, they close in, and eventually they circle in on one point. The red, green, and blue dots, they represent the alpha, the beta, and the delta. These are the lead wolves that everyone else is following. So this is how, just like in the last algorithm, we have different values being selected for the inputs. Each dot, it represents one guess at the best values, and the lead wolves are the best values we've found at any iteration. Over time, the dots converge towards, here are what the best values are across all of time. So now we got to look at the math, the details behind this visual analogy. How is this motion working? What's going on? This time it's going to be more complicated than last time, so just keep that in mind. You'll need to buckle your seatbelts. We have three categories of equations to talk about. One category, it's related to the position of each wolf. What I mentioned, each position, it represents some, input to a function. We have the equations that determine what are the best inputs, which ones lower the output the most. Those are going to be the leaders, the wolves that everyone else follows. And finally, how is that following done? How do we define the spreading far apart and converging over time to just one single point? So the first thing regarding position, let's again have W wolves, the first, the second, the Wth wolf, and each of these wolves, it will have some position associated with it. So let's say in real life, you have 3 dimensions, you could have a 3D position for the ith wolf, and that could be, go 5 in the X direction, 10 in the Y direction, 1 up. That could be something that works. Just to motivate this further though, to not just be, all abstract, I'm going to tie this into a particular cybersecurity problem that our team was trying to solve. The particular problem was our data sets that, had the incoming network requests, and we were trying to figure out an algorithm that could take the incoming data and decide, is this a cyber attack from a hacker or is this a normal user? The issue was that data set was 15 gigabytes, which is a lot, and it had like 50 features, 50 statistics about the incoming network request. And we did not know where to look amidst all of that information to figure out which information is essential. So we wanted to use this algorithm to select only the essential statistics and discard all of the other information. So the inputs that we had in that case, the guesses we were trying to make were which features are worth keeping around. And in that case, our position is not, a 3D coordinate, it's a bunch of zeros and ones. In particular, you have a 0 and 1 for each statistic, and a 0, it says throw away this feature. A 1, it says keep around this feature. To give you a practical example, in a simple case where you don't have like 50 statistics about network requests, which is hard to visualize, I guess. Let's take a dummy dataset D. It has 3 features, the length, width, and height of an object. If we say some wolf, it has a position vector of 1, 0, 1. We can use these ones and zeros to figure out which of these statistics from the dataset to keep around. In particular, let's define a selector function S. The selector function S takes in these zeros and ones because there's a 1 for length, length stays around. There's a 0 for width, width is not kept around. 1 for height, height is kept around. So this selector function, it can translate from the zeros and ones to the statistics that we keep around from the data sets. In this case, there were n total statistics, and out of them, we kept n feet equals 2. We kept n feet equals 2 total statistics out of the 3 total statistics. So this is what I mean about the position of each wolf, these vectors, representing which features we should keep from our data set so that we don't have 50 pieces of information. We can look at only the essential information. This seems fine, but we have talked this entire time about, function minimization. Which functions are we trying to minimize? We have just talked about the guesses. These x vectors, they're the inputs to our function, but what is that function? Well, we could just, make the function be the error. So let's say we define some error E. The error E, it takes in some, ones and zeros, runs them through the selector function so that it's left with some features. Then it will train some kind of, statistical model. It could be a AI model, it could be something else. It will create some kind of statistical model in a fixed manner, no matter which statistics are kept around, which features are selected. Now it's like a scientific experiment. We have some fixed statistical model that is training on the selected statistics in a standardized way. And we just see if we vary which features are sent in, which features are kept around, what is the final error we get from the model. If the error is higher, then we selected a worse set of features to keep around. If the error is lower, then we selected a better set of features to keep around. For example, in this case, this 0.23, it means 23% of the time, if we're training with the length and the height, we are going to get bad predictions. 23% of the time, we'll take an incoming network request, classify it as, a cyber attack when it's normal, or classify it as normal when it's a cyber attack. So if we wanted to, we could just make this, the function that we're trying to minimize, make it f of x, because why not? And multiply it by some real number k, just like, in the last algorithm, we had settings, parameters to adjust. So do we in this context. Now, the issue with using this particular objective function, this particular function to minimize, the issue is that we haven't given the algorithm any incentive to select only a few features. We've just said minimize the error. Okay, why not do that by selecting all the information? More information is good, right? Well, if we want the algorithm to solve our team's problem, that we have too much data, we need to get rid of data, we need to select only the essential features, we have to bake that in to this function being minimized. So what we're going to do is we're going to add in a new term that makes it harder to minimize the function if you select a bunch of features. For example, in this case, n feet, the number of features selected is 2, the number of total features is 3, this fraction is 2/3. If it selected all the available features, that would be 3 out of 3, that would be 1. 1 is greater than 2/3. As you can see, this function's output is getting higher when it selects a lot of features now, which means that if the algorithm wants to minimize the number of features, it also, if it wants to minimize the function, it also has to minimize the number of features. You might be wondering about this k1 minus k thing. K is just a number between 0 and 1. If it were set to 0, you could see the first term, 0 times this, it disappears. So the algorithm's only incentive is minimize the number of features selected. If you set it to 1, then this 1 minus 1 term disappears. So then you're left with only the error function as an incentive. If you set it to somewhere in the middle, now you're balancing the incentives of getting a low error, making sure you're selecting good statistics to do the prediction we want, and also making sure we only select a few features, not the entire dataset. So that is the majority of the equations, except one very hairy last equation. All of the setup we've done so far, it's kind of led to a trial and error algorithm. We have a bunch of random wolves, we just initialize their positions randomly, just give them a bunch of random ones and zeros. And we have a function that we can test to figure out, is this a good bunch of random ones and zeros? Or does it represent good features being selected or not? Which is, fine, but it doesn't encompass that movement of the wolves, that movement of start far away, gradually converging to just one point. So how do we model that movement when we figure out, which zeros and ones are being checked? Which wolf positions should we check? The first thing to model is that following behavior. The following wolves, the subordinates, they just follow the leader, the alpha. So we could just, take the intuitive approach. The alpha position at 10 seconds, the ith wolf that's following the alpha, it will end up there at 11 seconds. Seems straightforward. Does it get the job done? No, it doesn't. So the issue is that if we just, left it like this, let's say you have a bunch of wolves that start like a kilometer away from the alpha at 0 seconds. By the next second, at 1 second, they will all just directly zoom into where the alpha was. That is not like a gradual convergence. That's just like zoom. So we need to make this equation update more gradually. How are we going to do that? What we're going to do is we're going to add a parameter, just another variable. This thing is going to be called C. It's going to kind of throw off where the wolves end up. So they're not directly going to the alpha's position, they're going to the alpha's position minus a little bit. And that little bit, it will depend on the phase of the hunt. So at the start of the hunt, this little bit, it will receive, time equals 0. If it receives time is equal to 0, then this m, it's the maximum number of, it's the maximum amount of time that the algorithm can run. So time equals 0, and let's say the algorithm can run for 100 iterations, then this is going to be 2 times 1 minus 0 over 100. I said that fast. So 0 over 100, that's just 0. 1 minus 0 is 1. 2 times 1. At the very start, the algorithm will have this parameter equal to 2. As the hunt goes on, as the number of iterations goes on, then you can see this t gets higher and higher. Eventually, you'll get all the way to 100, which is the maximum number of iterations we've defined. Then you'd have 100 divided by 100, that's 1. 1 minus 1 is 0. 0 times 2 is 0. And then this thing, it disappears. Then you're back at that behavior where the wolves just hone in precisely on where the alpha just was. So as you can see, this parameter, it starts off at 2 and then it goes down over time. As it goes down over time, it makes the ith wolf follow the alpha more closely. We still have an issue. In this case, if we say that the ith wolf is doing this, that means that the first wolf is doing this, second, the third, and so on. All the wolves are doing this. This is kind of a problem because, why bother checking the same solution by getting all the following wolves at the same position? It doesn't make any sense. If we have like 5 wolves ending up at that exact same position, we only need one of them, and we want the rest to explore, related but different positions. So how do we achieve this in our equation? We need to add in randomness, just like we had those random R1s and R2s in the particle swarm optimizer. To add in that randomness, we make a vector R1 that just has a bunch of numbers between 0 and 1. You multiply that by 2, you have a bunch of numbers between 0 and 2. Subtract away 1, you have a bunch of numbers between -1 and +1. And then you multiply it by the bigness constant, closing in. Now you have a random negative sign in all the vector positions, and you have, some number between 0 and 1 to scale things. So this randomness, it makes sure that all of the wolves, they don't just go to the exact same points, they go to some point near, but not exactly at each other. There's still one final issue that's present here, which is that none of this takes into account where the ith wolf currently is. It could be that the wolf is 1,000 meters away. It could be that it's, 10 meters away. We don't want those wolves all traveling the same distance because, jumping from 1,000 meters away to 10 meters away, that would be teleportation, and nature kind of frowns upon that. So we're going to make sure our wolves aren't teleporting right near where the alpha is, regardless of where they currently are at. Each wolf will have to travel a different distance. So we create this new term, which looks ugly, I know, but it's not too bad. So this X alpha, that's where the alpha wolf currently is. This Xi, that's where the ith wolf currently is. You take their difference, you're figuring out how much distance between the alpha wolf and the ith wolf, multiplied by some randomness again, just to make sure that each wolf isn't moving the same distance on each iteration. And now you have another kind of scaling factor that makes sure that different wolves, they move different amounts, and the amount they move is dependent on how far they are from the alpha. Once we consider all of these terms, just a summary, the first term, the alpha, that's the target, that's where the ith wolf is trying to end up at. The second, bit, this multiplication, it determines how much error there is in following that target. The wolves don't precisely get to the alpha until the end, where, C becomes 0. And then this last part is how far each wolf moves in each iteration, and that has some randomness in there so that not every wolf is moving the same amount in every iteration. Keep in mind, C will eventually become 0, so all of this complexity will go away, and you will just be left with what we originally started with, which is the ith wolf at the end of the hunt is just following the alpha. So that is our big, messy, complicated equation done. This is how we define that convergence behavior. Spread apart, slowly get together, and close in on one point. Just one last, tidbit. As we said, there's not just the alpha wolf. There might be the alpha, the beta, and the delta wolves, the top 3 wolves in terms of leadership. So the ith wolf, which one does it follow? The alpha, the beta, or the delta? Well, we can compute where it would go if it were following the alpha, where we're following the beta, where if it were following the delta. Just means replace the beta and the delta wherever you see an alpha. Figure out where it would go in all 3 of those scenarios, then take the average position. That's where the ith wolf ends up. That is all the equations done, finally. Wow, that was a lot, yeah. So this algorithm is more complex than the particle swarm optimizer. Now, one thing that I didn't mention earlier, what are these alpha, beta, and delta? These are just the values that best minimize the function on each iteration. So we're saying, all other wolves honed in here, we found good prey in this position, but good inputs that minimize the outputs. So after all of this complexity, the big question is, what about our problem? What about, taking our 15 gigabyte data sets with 50 statistics and just figuring out what is the essential information in there? Did we solve it? Because I'm giving this presentation, the obvious answer is no, we did not. To be honest, I was quite frustrated when we did not at first, because it took me a week of debugging, a lot of math, lots of experimentation with parameters, settings, graphs, tables. But after a very, very long time that I described in this blog post, I figured out what the problem was and fixed it. So the problem in the earlier GIF I showed you, these wolves are moving very continuously. The inputs that they're adjusting, they're continuous variables. You could have a pi in there, you could have a square root of 2, set x to like 7.387459, whatever you want. So the wolves, they can move very smoothly. They can move in their tiny region just around the alpha and explore it. In my case, remember, the inputs, the positions are just zeros and ones. So you can't really vary those like subtly. You might have, let's say, an alpha, this 1, 1, 1, that's the vector. You might have an alpha, that's the best solution you found, include all the features. You might want to explore the tiny region around that as defined by the sphere, but you can't do that because the data is too discrete. You have to completely include a feature by setting it to a 1 or exclude a feature by setting it to a 0. There is no in between. And in this case, when you have data so discrete, the gray wolf optimizer doesn't perform very well because it's difficult to explore diverse solutions around a region. Solutions that are, kind of similar to the best, but not quite. In this case, the solutions are very different because they have to completely make a step change, a 0 or a 1. With this realization, I actually realized I needed another bio-inspired algorithm called the genetic algorithm to do the job better. I'm not gonna go through another half hour of that algorithm. Suffice it to say, it did work. Out of the 50 features, I ended up with just selecting the 21 best ones. After a lot of frustration, but a lot of learning, the genetic algorithm did end up getting the job done. The question is why, if that algorithm worked, did I present about the gray wolf optimizer? First of all, I think it's cooler. Wolves, they're nice genes. I don't even know what to visualize. But second of all, I learned so much more when working on the gray wolf optimizer because of those weeks I spent debugging, changing parameters, figuring out exactly how every part of the algorithm worked and why it wasn't a good choice for my problem. Compared to that learning, I didn't get very much from the genetic algorithm. And just, second try it worked because I'd learned so much more from the first try. I'd ironed out most of the bugs that were possible. That's kind of why I like being on the team. It's very different from, being in a university class where someone's just like throwing information at you and they don't care if you've gotten it or not. When I'm working on the design team, I'm tinkering around, I'm trying different solutions, something works, something doesn't, I'm very frustrated, forced to research, forced to try new solutions, but in the end, I get a much better sense for when I should apply a method to a given problem instead of just, here's how the method works. So that's the big point of the presentation. No more checkpoints, we are done. And I hope that you're more curious about bio-inspired AI algorithms as a result.